Bonjour tous. Je suis Dan. Je souhaite que je peux faire mon parole en français, mais malheureusement, je ne parle pas en français, donc je dois faire en anglais. So is that okay with everybody? If you can't understand what I'm saying, just shout out more très fortement, and je répète. Okay? No, plus bruit que ça. Okay, so my talk today is going to be about Solidity, and it's called Solid in Solidity. I'm going to attempt to educate you all in the world of blockchain and smart contracts. So hopefully it's an informative talk that you'll take something away from on a practical level. This slide got a really good reception last time, so I'm going to show it again. This is what Jan used to look like back in the day. So yes, as it was mentioned, I'm a web developer, so I'm coming from the angle of being in web development for a number of years. I don't know very much about blockchain, it's very new to me. I'm quite a creative person, I like to play with things and I like to try new technology. I'm from England, you might have heard about us in a history book. We used to be a country that existed. We're doing fine, thanks for asking. There's absolutely nothing to worry about, everything's going swimmingly, thank you. And we've set up a company called Vega, and Vega is attempting to solve a very innovative problem of creating a peer-to-peer protocol for financial products based on blockchain technology and distributed ledgers. So we're trying to create a system which is fully decentralized with no exchanges, no banks, no middlemen who are going to be costing you more in your transactions, and people that you have to crucially trust in order to perform your financial trading. So we're trying to solve a number of engineering problems all at the same time, but the goal is to create a marketplace where, for example, you could buy futures in Bitcoin, or you could have options in various fiat currencies as well. So it's not just about crypto, it's about smart financial products, and that's the focus. So in a nutshell, the way it works is we are developing a P2P system which uses Go as its underlying tech stack to create a fast network that can reach consensus a lot more quickly than Bitcoin and Ethereum can, but using the Ethereum blockchain to lock up all the collateral that we're storing so that there is no risk of anyone committing more funds than they can actually process. So the focus of my talk today is on the Ethereum side of things, but the actual stack is all about trying to reach a consensus with other nodes as quickly as possible and just keeping the smallest amount of smart contract code as we can. And this means that anyone who has an Ethereum wallet can actually participate and make trades. So if any of you actually have Ethereum, does anyone actually own Ethereum here in the audience? Okay, there's a few of you, that's cool. So if you've got an Ethereum wallet, you've got an address, you should be able to put that money on Vega's table and say, I'm willing to stake that money, and you can trade from anywhere at any time, and you don't have to trust Vega. We're just a protocol, like Ethereum. Smart contracts is just a protocol. You can use that software for your trades, and we can't steal it from you. We don't charge fees for processing, so we're just providing the tools for you to go and use. If you want to find out more about us, this is our website, vegaprotocol.io. There's more information there, so watch that space. So today's talk is really trying to just get across a few basic concepts about smart contract technology. So what I'm trying to say to you is basically there's this thing called smart contracts, which is built on blockchain technology, specifically the Ethereum blockchain. And Solidity is the language that's used to write them. So I'm going to be showing you some Solidity code. I'm going to give you a gist of how it works. It's hard to understand at first, so a lot of you might be cynical about this technology, or you might be scared by it because it's involving cryptography and all these other jargon, scary words. But after a while, you can actually bring a lot of the knowledge you already have as developers into this space. So I'm going to try and show some object-oriented principles that apply to Solidity, and you'll find that actually a lot of those principles actually carry across. So you can write smart contracts too. Yeah? So give it a shot. So you need to start off with some core concepts. So this word blockchain is very trendy. 6 months ago, I hear the word blockchain and I'm like, I've no idea what any of this is doing. It's like magic. It's this kind of weird system that I'm assuming does interesting things. And then somehow this blockchain has smart contracts built on top of that, which automatically allow you to do things. And I'm looking at this and I'm thinking, I have no idea. And as I've mentioned before, I've got a background in tech. So I'm coming at this from a developer's standpoint. And a lot of this technology just did not really stack up for me. I didn't really understand what it was doing. So if I was to try and put simply what is a blockchain, it's really just a distributed database that once you write to it, you can't change your mind about it anymore. So if you want to make a change, you've got to make another write. So in my brain, I'm thinking like, it's a distributed system, I write to it and I can forget about it. These transactions get appended to this log and distributed around the network, and that's where the chain word comes from. So each transaction is chained to a previous state. And then globally, via some very clever algorithms which I'm not going to go into, it's way beyond the scope of this talk, we can verify that those transactions are the same so that all of the participants in the network can agree that's what actually happened. And that enables us to then talk about smart contracts, which in the Ethereum blockchain are basically bits of code that are stored on the blockchain and some data that's going with that code to act as its state. So those two things playing together enable us to write some snippets of code, and they sit on the blockchain at a specific address so we can target them. And Ethereum doesn't make any distinction between a smart contract and a wallet. It's just an account. It has a balance, it has an address, I can send ether to it, I can receive ether from it. So in a certain sense, I mean, coming from a SQL background, for example, I think I've already said that, it's almost like a store procedure, right? So if something triggers this code to be run, something else gets automatically run in the network and it does stuff, okay? So it's not actually as alien as it might sound. If you actually think that, you're thinking to yourself, yeah, but Dan, how does it actually work? There's this wonderful phrase in the Solidity documentation, which is, don't worry about it, right? So there's a lot of magic going on, but you'll use Amazon, AWS, you don't know how that works, so it's okay, right? I mean, we was just talking in the lunch break about we use things like Apache every day, we use things like Postgres every day, and we don't always understand every last thing about it, but it's true that you can get started with Solidity and not necessarily know everything there is to know about blockchain. If I had to try and explain what Ethereum was, it's, in my mind, a little bit like going back to the beginning of computing, when it would look a little bit like this, and we had programs written in punch cards, and we would then put this punch card into a centralized computer at a university or an institution like Eurotechnology. We'd run our program and see the results. But it's just done on a global scale where there are multiple machines all running the same code. So you can think of the Ethereum virtual machine that runs the smart contract as one, ironically, centralized thing, even though it is distributed. Does that make sense? Or does that just confuse you more? So when you're thinking in contracts, you can't think about classes that exist. You've got to start thinking about transactions. It's a very specific use case that smart contracts are trying to solve. We're sending ether balances from one address to another. And so the sort of use cases that you're going to use smart contracts for will tend to be financial, but they don't have to be. There's lots of interesting applications of things like insurance, legal documentation, and so on. But ultimately, there is a very centralized idea around transactions, accounts, and balances. And because of this consensus, and because of the fact that all nodes have to run all the smart contract code, these operations are relatively expensive. I mean, there are 17,000 nodes running Ethereum. If I write a smart contract that says what is 2 plus 2, we've got to run that code 17,000 times to get the answer 4. That's fantastically inefficient. It's actually pretty stupid. But what we get in return is we're very, very sure that that's actually the answer. So. Similarly, storage space at a premium. We can't just put our entire SQL databases into this because The blockchain has to be shared around the whole world, has to be cryptographically processed, and so there's a real premium there as well. But crucially, if you're a developer, you want to work in smart contracts, there are no objects. We don't have that sort of OOP paradigm. So if I'm trying to apply solid principles to smart contracts, we're going to get stuck a little bit because there are no objects. So I'm going to attempt to walk you through your very first smart contract code, and we'll see if we can make it better as we go along. So since we're at a conference, I thought maybe we could write a smart contract that models a conference, right? So what sort of features do we need? Let's say we want to buy tickets. Let's say we want to track who's attending the conference. We might want to have a democratic method for allowing any of you to submit a talk, a proposal, a call for paper. We could vote for which speeches we like the best, and then we could organize our conference that way in a very transparent way where no one can alter it. It basically means we don't need Jan anymore because he's a centralized node. We can all organize it ourselves, and it's all completely transparent and open. And you can have the weekend off, Jan. And if we get time, if I don't run out of time, we might talk about some tokens that we can make in Ethereum and have some fun with that. So if you are a geek and you want to follow along with this, all the code is on GitHub. So please send me pull requests for all the mistakes I've made. It's on github.com/Vega Protocol, solid in Solidity. It's on my Twitter as well. If you, there's a little treat for you if you follow me on Twitter. And all the stuff's there if you want to study this. There's going to be quite a lot of code moving pretty fast, so it might be best you do it as your homework this weekend, okay? So let's start off with a really simple smart contract. It looks a little bit like this. For those of you in the room who are JavaScript developers, you'll probably notice that it's quite JavaScripty. That was a deliberate decision, just so that the syntax is somewhat familiar to new participants. We're defining an entity called a contract, giving it a name. And at the most simple, I'm thinking about this problem is, well, we've got this conference. It's going to have a price, and it's going to have a list of people who are coming. Okay, so I can define that in Solidity as just a number, so an uint, unsigned integer, called price, and an array of addresses, which are just Ethereum accounts, called attendees. And all this smart contract's going to let me do is create instances of it, because obviously Takeoff's going to come back next year, and we need a whole new instance of Takeoff. So we can instantiate new Takeoff conferences and give it a price, and that will then get stored in the contract, so that once we've created the conference, no one can change the price. You can then introduce a function which says, I want to buy a ticket. So how do I buy a ticket to the conference? Well, as long as you've got enough money, right, you can come in. That's basically how buying stuff works. And if you've given me too much money, I need to give you some change in return. So I can express that in about, 4 lines of Solidity. I can say that if you're trying to buy a ticket, you've got to make sure that the value of Ether that you're sending me is bigger than or equal to the price. If it is, you're going to go on the list of attendees. If it isn't, then you're going to get an error. But if you do, you'll get on the list. And then if there was any extra money, we'll return it back to you as change. Okay, so pretty simple, but nothing too rocket science about that. And I suppose if you want more detail into how the runtime works, that will probably be something that for another day when we can say, how do I actually physically call functions and send Ether? But if you've got a wallet, you can basically call this function very straightforwardly. Suppose I wanted to add another feature, like I want to submit a talk. Well, Solidity actually has support for structs. So I could create the concept of a speaker, who is basically just an address. So my Ethereum wallet effectively represents me as a speaker. I might have a title for my talk, like Solid in Solidity. And then the contract will just keep a hash, like a mapping, of which addresses map to which speaker. So in that sense, we can think of it as being a list or a hash in other languages of all the speakers who are participating. And all I've got to do to submit a talk is to provide a title, and I can then create a speaker struct, passing in all the values, and that will then get stored in this global hash, so that the person who is submitting the talk knows which talk is being associated with which speaker. So that's probably as close to an object we're going to get, these structs. And it's just a collection of data that we can then store. And that data is stored on the blockchain. So all of these mappings between who submitted what talk will get stored on the blockchain, so I can't just screw with it later and get rid of someone's talk. Okay, so those are some basic constructs. How do I get more complicated? Well, let's say I want to start voting. I want to be able to say, out of all the talks we've got, I want to vote for a speaker A, B, or C. We could introduce a function called vote that just takes the Ethereum wallet address of a speaker who we know has submitted a talk already. We just make sure that you can't vote for yourself because no one likes a vain person. We need to make sure that you've actually bought a ticket, because if you haven't bought a ticket to participate in this event, well, we don't want you to vote. So we might devise a system where we could say, you didn't buy a ticket, and I'm going to iterate over all of the attendees in the array. If I find you in that list, then I can say, right, you've bought a ticket, so yes, you're allowed to vote. And then finally, we could then say, well, I want to make sure that you've not voted twice, because that would be undemocratic. So we could then say, go and find the speaker in the map. If you've already voted for that speaker, well, sorry, you've voted already, so we're going to give you an error. Otherwise, we'll increment it by 1. So on the face of it, this is actually quite straightforward logic. It's just trying to wrap your head around how this gets run and when is actually the hardest part. So hopefully so far I've not said anything that's going to scare you off, but it's a couple of if statements, a couple of loops, and it's pretty intuitive stuff. So once we put it all together, this is our hollowed out smart contract. It's just a little reminder, we've got a contract called conference, we've got a price, we've got an array of addresses, we've got a struct called speaker, and we could then put all that code together and say, well, the speaker keeps track of which Ethereum addresses have voted for which person, and then we can have a number of votes and put all that code together. It doesn't quite fit on the same slide, but we can fix that. Now, there's nothing intrinsically wrong with this code, but as a developer, I look at it and think it's a bit verbose, it's a bit long, it's a bit repetitive, and I wondered to what extent could we apply our existing knowledge about OOP. So hopefully, has everyone actually heard of the solid mnemonic? Yes? Okay. So everyone's probably heard of the S in solid, that single responsibility principle, and time again, whatever language you're using, you're being told to always follow this principle. Don't repeat yourself, keep your code dry, and all the rest of it. So the single responsibility principle is pretty straightforward. It just says, make there only one reason for your code to change. Okay, so in the case of a contract, don't have code in there which is doing different jobs. Just make it do one job, and one job well. And another way of thinking about this question is, what does it cost to change? Like, what would the side effects be if you did change this contract or this function? Would that have a knock-on effect on any other code that you've written? And so really, it boils down to just encapsulating your code well. We're trying to look at the coupling of our code and make sure that we don't end up with too many connections. So one of the weapons we've got in our arsenal is, in Solidity, is this idea of an internal function. So we have the ability to have function scope. We can say things are public, which means we can call them from an Ethereum wallet, or they're private, or internal is the jargon, which means that only the contract itself can call them. So just by splitting out the code into these separate internal functions, I've actually made my buy ticket method a lot more readable. I've said that buying a ticket basically means checking that the value is bigger than the price, and then you can register the attendee and give some change. So by putting them in separate functions, it's very clear which function is doing what purpose it has. It's a lot easier to test. It's shorter, more readable, etc. Similarly with the voting code, we can simplify that a lot just by saying, well, let's create extra methods when we're doing different tasks inside our code. So the vote method was saying, I only want to vote if you're not voting for yourself, if you haven't already voted and you've bought a ticket. So if I start creating functions called has not already voted and has bought a ticket, then we can just simplify the vote method to say I'm requiring you to have bought a ticket, I'm requiring you to have not voted. And again, it's making the code more readable, more reusable, And of course, we're obeying the single responsibility principle, so that's all good. Once we've got these internal functions, Solidity actually allows you to transfer them in something called a function modifier. So a function modifier is a special kind of function that can be used as a precondition on your contracts. So you're not actually going to run any of your functions until those preconditions are met. So just by rejiggling that same code a little bit, I can create what's called a modifier. It's called, if this vote is for another person, have you not already voted? Have you bought a ticket? And then you'll notice towards the bottom here, the function vote then says, I'm only going to vote for this person if the vote is for another person, you've bought a ticket and you've not already voted. So you can actually make your functions very small, very discrete, and simple, and you can put more preconditions in place to prevent that from being accessed. The other way we can use the single responsibility principle is separating out the contracts into more contracts. So rather than thinking about your Solidity contract actually as one legalistic agreement that you're entering into, you can actually think of it just as a construct that you can create, a little bit like a class, but it's not really a class. And we could then start creating contracts that just do one job. So suppose I thought of this conference as being a ticket-based event. It's just an event you can buy tickets for. I could reuse this conference for this contract for a concert, or for a wedding, or whatever you want to do that you buy tickets to. And I can then encapsulate that code into its own contract. I could make another one for the voting stuff. So I've got a contract called, this is a democratically electable speaker event. So that's a sort of event where anybody can vote for the speaker. And I'm putting that functionality into its own buckets so that I can then compose them again later in a very concise syntax in Solidity. I can say that my contract conference is now a ticket-based event that's democratically electable. And this is just an example of using good old-fashioned inheritance to bring in the functionality from the other contracts. So contracts can extend one another, and that then enables you to compose the functionality that you need based on your own requirements. So already we've managed to simplify the contract quite considerably just by obeying the single responsibility principle. Right, I've left myself 8 minutes to do the other 4. So does anyone actually remember the other 4? Because they're the most complicated ones. Right, O in Solid is the open-closed principle. And it's pretty straightforward. I mean, it's the sort of principle that you ought to intuitively use in your coding. Whether you do or not, I don't know. But the official definition of the O in Solid is that your classes should not be modifiable by their subclasses. So I can extend your contract with inheritance, but I can't modify the existing one. So this is basically saying don't screw with a method after you've defined it, because you could run the risk of changing the behavior. So when we're using inheritance, this is actually a problem. So suppose we wanted to make our events more generic, and I wanted to create a contract called event, which is going to be the super contract for all events that you can ever attend in the crypto world. All I really care about in the event class is that you can attend it or not. I'm not saying anything else about it. We could then create subtypes of those events, and we could say, well, a ticket-based event is just an event. Okay, it's a kind of event. It is an event. And we could then create like an event called an invite-only event, where I can only come to this event if I've been invited beforehand, and I'm on this list of invitees. So under this contract, it's still an event. So I have access to my attendees, but I've now got a list of invitees as well. And unless I marry those two lists up, I'm not going to be allowed to come. Now, if I was to write code like this, it would work fine. But suppose then I wanted to add some code to the event contract, which then had to have knowledge of its subcontracts. And this might happen if I might want to write a function called total proceeds, which says, well, how much money have we raised from all of the events that we've organized, regardless of whether it's a ticket-based event or an invite-only event. So suppose I had an array of event objects being passed into a function. I might be tempted to write code like this, where I'm iterating over that array, and I'm trying to figure out the type of that subcontract in my code. Now, any of you who's a developer might look at this and say, this is not very good, because every time I add a new subtype of contract, I've got to change this code. If I rename my contract, I've got to change this code. If anything about the subcontract changes, I've got to change it because I've got this coupling problem. So this code does not obey the open close principle. And instead, what we should be doing is extending events so that we actually know, we're letting each subtype know how it should respond to certain methods. So a better approach might be, let's create a method called sales on our contract, and everything that's an event will just know how much money it's made. And then if I need to override that method in a subcontract, like the ticket-based event, I could say, well, in the case of a ticket-based event, sales is just defined as the number of attendees times the price. And so that way, every time a new subtype comes along, it just knows what to do because it's going to implement the sales method. This is probably where most people get off the train with Solid, and they think, what's the L bit? Well, the L is actually for Liz Conf, who is one of the more preeminent women in tech who we should be all celebrating. Very clever woman who also was the L in Solid. And put simply, I mean, you can read very complicated papers on the Liskov substitution principle, but it's just saying that every subtype should be interchangeable with its supertype. And really what that means is that every contract in our ecosystem should really live up to that ISA relationship. It should say, the ticket-based event must be an event, and I can swap out an invite-only event for a ticket-based event, and everything should just work. Otherwise, I'm not really following the Liskov substitution principle. So another way of thinking about this is just that all the preconditions and the postconditions match up. And if they do, I should be able to swap out every subtype for another subtype, and everything should just work, TM. So a classic example of this in the Ethereum world is you can actually create your own crypto assets called tokens. I don't know if anyone heard of crypto kitties and things like that. Well, they're just tokens are just contracts which accept Ether. And if we want to create an environment where I can swap these tokens for other tokens, all we're really saying is they have to have the same characteristics in Solidity so that I can swap out one kind of token for another. And so in the Open Zeppelin project, which you can read about, it's an open source initiative to create reusable templates for smart contracts. There's a standard called ERC20, which is a way of standardizing these crypto assets so that I can interchange one for another. And this is actually a really good use of the Liskov substitution principle, because I can now write code in my contract that says I could accept an ERC20 token as an argument to my buy method, and I know that it's going to have methods for allowance, transfer from, because they are part of the standard. So in theory, I could pay for this conference with any ERC20 compatible token. When you see that going badly, is if you start to change the behavior of functions in a subcontract, you're not really following the spirit or the documentation of that function. You can actually end up writing code which doesn't really follow the LSV principles, but it's actually quite hard to do. I mean, what I've shown you so far is a bit theoretical. I mean, if you just do things in a straightforward way, it's actually quite hard you actually have to work against yourself in order to run into this problem, I think. And this ERC20 token is perhaps also a use of the I in Solidity, which is the interface segregation principle. And the interface segregation principle is just saying, code to your abstractions, right? Don't just write new methods in every class that you create. Just code to those interfaces instead. And so here's actually what the code for ERC20 looks like in Open Zeppelin. It's just a few function definitions which explain that every token has an allowance. You can transfer from it. You can improve transfers between accounts. But the actual implementation of each token will go down to each individual developer. So if I code to ERC20, I can actually interchange those tokens for one another when I'm writing smart contract code. And so the example implementation of this in the open source project, Open Zeppelin, is called the standard token. It uses inheritances to say, well, a standard token is just an ERC20. and it will then implement how transfer from works, which will just say I want to move balances from one place to another. So if I want to create my own token, I can just inherit from this, and I'm all ready to go. Suppose I did want to create my own token. I've got 41 seconds to do it in, called Conf token. All I need to do is sub-inherit from standard token, and I can start then adding my own functionality. And I might want to add functionality such as, I want to give away some tokens because I'm feeling generous. Well, if I write code like this, I'm not really following the principles that I've just set out because we're extending each of the code. So the last one, D, I'll throw it in for good measure, is dependency inversion principle, which is saying swap that relationship around. So rather than putting your code inside of the original contract, we could create a new contract called a token giveaway that takes your ERC20 in as an argument, and therefore we're putting the dependency in. So basically the upshot of it is that Solidity is pretty solid, okay? So it's worth applying your object-oriented principles to it. All of that can be brought with you, and you should give it a try. Thank you very much. P.S. We are hiring.
I don't think we've got time for questions, because
Okay.
if we are just avoiding, like, wasting time showing pictures, old pictures of me during a presentation and saying, oh, je suis Daniel, voilà le vieux photo de Yann, je vais faire le contrat, il va remplacer le organizer de takeoff. Thank you anyway.